Welcome to the Math Ed Podcast. My name is Sam Otten from the University of Missouri, and joining me again is one of my favorite guests. It's my friend Julie.nurnberger.haag. Julie, thanks for being back.
Thanks, Sam, I thank you every time. Thank you for doing this service to our field. I can't believe you've kept it going.
Well, the good work keeps coming out, and it's fun to talk about it. And you've been doing some work that I always enjoy, which is related to children's shape and the way that we experience shapes, especially in the early years. You, in the past, talked about children's shape books, like the picture books that show triangles and squares and circles, and you did some analysis of those, and you uncovered some aspects of the books that might contribute to possible misconceptions. And this has been an area of study for you for several years. And your new article came out, and I'm very happy to talk to you about it. And this work comes out of your time at Kent State University. It's called Simplest Shapes First, but let's use cognitive science to reconceive and specify what simple means. And this is in Mind, Brain, and Education. And it's available actually open access, so people can get it. I'll put a link in the show notes. But Simplest Shapes First. Speaking of shapes, I alluded to some possible misunderstandings of shapes that are out there in the public, not only amongst kids, but even amongst the general population. So I wonder if you could first set the stage about what are some of those shape misunderstandings or confusions that have motivated you to keep kind of thinking carefully about shape work?
One of the things, I don't know if you know, or if people who know me in the field know, that where I started teaching, I taught high school, but I was at a 1st through 12th grade school. So I'm really grateful for the range of experience I've had across my life that helps me think through these things across the lifespan. When I was teaching high school geometry to students with learning disabilities, I didn't think about what might have happened earlier, even though I did for number, until a teacher from the elementary school came down and said, "Isn't a square a rectangle?" And I said, "Yes." And they said, "They're teaching the kids wrong." And even once they understood and believed that it was mathematically accurate, they believed it was developmentally inappropriate to try to teach children this. Now, granted, this is 25 years ago, and it's been a really long haul for this line of work, because math ed isn't always aware of the early childhood needs, and early childhood isn't always as amenable to understanding the importance of math. And some of those issues are from birth. Their children are experiencing what I've coined as environmental math, which is a subset of environmental print that came out of my when I was getting my master's degree in learning disabilities and literacy. I took an emerging literacy course, and I'm like, oh, environmental print, that's what's happening in children's classrooms in early childhood and on word walls and things like that. Mm-hmm. So the shapes that they're encountering, the environmental math that they're encountering on a daily basis, is teaching them a trapezoid only looks like a certain way, which as math educators, we know is an isosceles trapezoid. Nothing else could be perceived as that.
Mm-hmm. You know, the higher shapes like the pentagons and hexagons are pretty much always regular. Let's say you start to just think, oh, apparently those octagons and hexagons are always regular.
Exactly. And then the 2D, 3D issue. So one of the things that the Common Core did do better than previous versions of things is that it said, okay, we need to get students to understand 2D versus 3D. Mm-hmm. But the children's books and other things, they'll show a picture of a cone, like an ice cream cone, and call it a triangle. Mm-hmm. They'll show a picture of a ball or a coin and call it a circle. There's so many things that are wrong, which is why there's multiple articles out on my ResearchGate about these things. And we talk about it a little bit in this article too, in case that's something that's new to a listener's thinking. Is there anything else you want me to bring up? Because
no.
you know I can go on about that, but we want to
makes me want to tell you actually about an article that I've written with some of my colleagues here at Mizzou that's about teaching shapes inclusively. This is for the mathematics teacher learning and thinking pre-K to 12, but we propose this activity with young kids where you put a whole bunch of rectangles together and you kind of start to just sort them and notice things about them, but you actually put squares in with the other rectangles, and you actually start with all of them together as rectangles. And then later you separate them out as squares and rectangles. But we say, like, no, it's important to actually have squares in there in the mix.
And that's what Van Healy said. So what happened is Van Healy he and his wife wrote their dissertation in the 50s in the Netherlands, and it wasn't translated into English until 87 or 86. And then the US started getting it. And so that's when it started to be thought about. And he absolutely, that is what we're supposed to be doing. We're not supposed to be withholding certain shapes or certain orientations of shapes. We're supposed to be giving them an authentic chance at learning.
But I'll have to maybe mention that one again when it comes out. We have it accepted. I'm not sure when it'll come out, but it's fun to just, think a little bit differently about how we approach the shapes. But you've thought about it a lot, and you also have this different way of approaching shapes. And in fact, a sequence of ways that you can kind of build students' learning for this. But before we get into your article that has this new sequence for learning shapes, I want to first let you say a little bit about the current situation for shape learning. So how would you characterize the current curricular approach to shapes? So not just the environmental math, the kind of shapes that students see all the time on TV or on YouTube or on picture books and posters, but like in the curriculum, how would you describe the current way that shapes are approached?
It's wonderful that in the Common Core standards that there was geometry emphasized, which wasn't necessarily happening in prior efforts. And it's obvious to those of us who are familiar with Van Healy level framework that those who were on the committee and or gave feedback tried to infuse the Van Healy level thinking into what is provided as a sequence. However, it really isn't implemented with the fidelity that Van Healy intended. And there's very little specificity and not a logical progression of which shapes are taught when. For example, if one searches the PDF for the word octagon, you won't find it. But children are taught octagon, the regular version of an octagon, since birth. And they see them at stop signs, but only the regular version. There isn't a logical sequence. What I think happened is that from the last 70 years of starting with the simple shapes, that they were simple to perceive. And that made sense based on what we knew and didn't know about learning and thinking 70 years ago. That we start with what's visually simple and then you move on from that. But we can't just move on from that because that's what is really at the core. If you're someone who's diehard constructivist, you might think of it as a schema. From different learning perspectives, you might see it in a different way. But that's what your starting point is then. And it's really difficult to accommodate new ideas if you're coming from a constructivist perspective.
And would you say simple to perceive, is that related to simple to recognize? Like they recognize it because it's kind of like the same sort of octagon or the same orientation of a triangle that they're used to seeing?
So the simple to perceive is a perceptual memory. It's easy to perceive it and memorize it in large part because it has multiple symmetries or it's always a certain look.
I see. Okay.
So that's why circles are easiest to learn at a visual level. Triangles aren't simplest to learn at a visual level, only if we only limit what they can see. And that's what's been done. They only get to see equilateral triangles. They only get to see acute isosceles triangles and often pointing up.
I was going to say it's not just which ones, but it's also always oriented with like a nice side along the horizontal.
Exactly.
Yeah.
And that's what my first study and everything after that points out about the orientation of the shapes. And the squares are almost always, even with some of the better authors, the squares are not included on rectangle pages. And if we look at textbooks, that also can happen. So when you look at the sequence and they say teach triangles, rectangles, squares, most adults don't know a rectangle doesn't have to have oblong sides. So if you memorize this template that a rectangle has oblong sides, that's visually easy to perceive, and squares are visually easy to perceive. But to define a square, it has to have 4 sides, 4 right angles. I mean, I'm actually not defining it. I'm using early childhood listing of properties, not necessarily sufficient. But the idea that you have to think about the angle size, not just the number of sides, and the length of the sides. And also the idea of rhombus. Rhombuses show up in pattern blocks, and they start being used in preschool, but only that one image of a rhombus And that's not specifically listed until later in the standards, but yet we know they're getting exposed to limited concepts earlier. And in the standards, the properties aren't foregrounded. It's almost as an afterthought. It says they should do this with shapes and talk about properties. For example, the number of sides. They don't say students should learn the number of sides and angles that these shapes have, et cetera, et cetera. So one of the issues is that properties are not foregrounded. So why would students think that properties define shapes? And that's actually something we see in adults on data I published with future teachers, that before analyzing the books with the rubric, they just thought you look at a shape and you get it from the way it looks instead of thinking about properties. And related to properties, a key issue that people in our math ed community would appreciate is think about defining properties and what a definition is in our standards. I don't mean standards like Common Core, but standards of mathematical reasoning, right? That number of sides and number of corners aren't the only defining properties. They aren't sufficient to define a square or a rectangle or a trapezoid. But these are the properties that are first taught to children, because those are developmentally appropriate properties to teach children.
Number of sides.
Yeah.
Yeah.
When it's concurrent with learning to count at all. So it really would behoove us to capitalize on giving them another authentic reason to count, integrating the shape learning. And this isn't just hypothetical. I've done this with 3 and 4-year-olds in a school. And honestly, the first time I went in, I didn't do that. I used Anglegs and I just had them make polygons and explore by just saying, I didn't tell them the term. I just had them put together shapes that couldn't have crisscross sides and it had to be closed, right? Giving them the properties. And they did beautifully. And I realized, oh my gosh, I am totally underestimating these kids. So that's when I said, okay, that's the first step. And so the next year I went in, we just jumped right in with, it has to have no crisscrossing sides. It has to be closed. And okay, now put them together and sort them into categories like it shows in the picture of the article of 3 sides, 4 sides, 5 sides, that kind of thing.
Right. And you can get more interesting 5-sided figures instead of just a regular pentagon, regular pentagon, regular pentagon.
Exactly. So if we're not giving them prefabricated tools like pattern blocks, like I really wish we would limit how much exposure to pattern blocks they have, or only pictures on pre-made worksheets, that they can create these varied, and it's an informal assessment that we can see if they're only creating the regular shapes and challenge them to make others.
Right.
Yeah.
Well, I feel like you're now leading us into the kind of the main purpose of the article, which is to propose a sequence for shape learning. And, this came from your experience and you started to have these insights. But you also brought together a collaborator. So I wonder if you could tell us a couple things here. First of all, what was your guiding principle for this sequence? And then, of course, we'll get into a little bit of the details of the sequence, and the article has a lot of detail about it. But first of all, what was the guiding principle for that sequence? And then also, how did Clarissa Thompson come in as a collaborator on this?
Yeah, so almost since the beginning of realizing the inaccuracies of shapes, I wondered, well, what should we be doing? And there's a 1987 master's thesis that still gets cited because so few people have done this work, where she taught first grade, or the person, I can't remember gender, they first taught square rectangles to show it could be done, and that a square could be a rectangle. But that's a very limited slice of it all. And as I learned about Roche, Rosch, and colleagues who do category work in psychology, I was base level, subordinate level, and subordinate level. This is all about categories, right? So I was trying to apply that psychological knowledge that we had about how people think. And I couldn't figure out, well, what would be the base level? Because in natural categories from Roche, the base level is easiest to learn. And the things that are in that category are more similar looking than each other. But in real life categories, natural categories, there isn't a definition. It is based on perception. Whereas in math, our shape categories are supposed to be based on properties and definitions. So it was many years and the experiences of finally working with the almost youngest learners that I started realizing kind of where could we start with this actually? Instead of trying to fit in where would we go next based on what's been done for 70 years and switching things around, what would be the ideal if we just pretended there was a shape utopia and they weren't being taught wrong in other ways? What would the ideal be? What would give them the best chance to do what Van Healy intended? And so from that, I worked out that we should be focusing on properties and which properties could we begin with, which appropriate 2, 3, 4-year-olds. And so curved and straight, I mean, even Piaget worked on that, right? So that is the very first column, is starting to think about that as a property, but yet that first column of figure 3 of the property-based sequence is also includes visual levels, right? So the contrast between a 2D shape and a 3D shape is still at this point at the visual level or syncretic level, which so many people avoid or ignore, which has been around since 86 or 87, Berger and Shaughnessy. And we really need to not focus so much on the visual level, which is a very old framing, but syncretic is a new meaning that includes at least a property piece. And then moving into like the anecdote I just told you about the students, 3-year-olds can totally handle putting together shapes with the right tool, like an angleg or an explorogon, that is not open and doesn't have crisscrossy sides, to use early childhood language, and then counting the sides and sorting them. And that means they're mathematically accurately defining triangles, quadrilaterals, etc. And we know they love big words because they know dinosaur terms. And oh my goodness, you should have seen how excited the kids were when we talked about spheres. And I didn't intend to talk about spheres. A child just noticed a semisphere that was holding up a sign that I had for something we were doing. So then we had to talk about them. So that's the second column of the property ideas. And then I really tried to think through, well, what would be the next step? Now, a lot of people, I bet, are going to say kids can't understand parallelism. That's too complicated for this as a third step. But Van Healy used the idea of railroad track sides. And also, I do work in embodied cognition, even though this you might not be noticeable in this work. If you have students make parallel sides with their arms, they can start to find parallel sides by not using the formal term parallel, but railroad track. So that's why I decided that. One of the reasons I decided that was next, that it is actually developmentally appropriate. Mm-hmm. But also because that allows us to develop the hierarchy correctly, that we're starting with the broadest category and working our way down, that we get parallelograms before we get rectangles and before we get squares and rhombus. I did debate about the right angle, about the angles versus sides, because it seems like the length of sides should be easier. However, if we think through what does it mean to know that two sides are congruent and compare them, requires not only measuring length either specifically or indirectly with a tool and then comparing it to another, you actually have to use the transitive property conceptually in order to know if I take this and I make a mark here and then I move it here and the mark is the same, then that means these two sides are the same length. But if we don't use protractors, that we shouldn't be using protractors to begin right angle, obtuse angle, acute angle instruction. If our third category is just, is it a right corner or bigger or smaller? There's one tool, a right corner checker, which I believe I also got from Van Healy, compared to the angle you're checking. So there's one comparison to make, and it allows us to build the hierarchy from broadest to most specific. If we actually, in an idealized world, could hold off on squares and rhombus until after we talk about right angles. So I thought through these things, and I had these ideas from several years ago of categorization and thinking that a lot of what I'm seeing in the standards are too much still based on behaviorist and information processing instead of what we know in cognitive science now, and underestimating students on categories. So I reached out to Clarissa, who studies math cognition, but hasn't done anything with shapes yet. And because I hadn't been in the lip for so long, I knew it would take me too long to get it out if I did it on my own. And I also knew it'd be better if we could write it for a psych, not a psych audience, but a psych amenable audience, right? Mind, Brain, and Education is read by a more diverse audience. And so I was fortunate to partner with Clarissa. And so also by working together, it helped me think through how to keep informing adults. How do we talk to adults who think they know their shapes, especially possibly researchers who are using shapes in their stimuli in experimental studies? How can we possibly also affect change in that way? That it's not just the children's books that might be communicating things inaccurately. And so Clarissa and I are just a great partnership, and looking forward to figuring out our plan to test the sequence more formally.
Yeah. Well, speaking of, sharing the shapes and having some visual elements, again, I want to let people know that this article is freely available. So if you look for Mind, Brain, and Education, you'll be able to find it. I'll put a link in the show notes. And there's a figure 3 that I want to ask you about a little bit more, Julie. So you were alluding to some of the levels of it, but I wonder if we could just talk through it again.
Awesome.
That figure has this property-based shape sequence, and it moves from defining the properties of polygons themselves to going through some critical properties in an organized way, but it has quite a bit of detail to it. So, reading the article definitely helps flesh this out. But maybe if you can just walk us again through some of those steps, and then I might probe a little bit as you're talking. And I'm looking at figure 3 while you do this. So if the listeners are able to pull it up, that might help as well.
Yeah, definitely. The way I organized this was first by 2D shapes, which is pretty much how everything in the curriculum is already organized anyway. 3D shapes don't get enough attention in the standards. But as I thought about, okay, if I'm going to create a property sequence that has both 2D and 3D, how does this work? So I started with what makes sense for the trajectory of 2D shapes. So what I mentioned is starting with the 3-year-olds with polygons with tools like the Anglegs. And then the next step is the N-gon named shapes. So triangles, quadrilaterals, pentagons, hexagons, septagons. Yes, they could handle it. Why would we skip over that just because it's less common in the environment? Octagon, of course, we can't stop before octagon, unlike what the standards say, when they're perfectly capable of doing 8 sides and they think it's fun.
Yeah, and they like spiders and octopus, and
yeah, exactly. And that's the thing with during my master's degree, I became certified in reading too. Exactly. All the more we should be using prefixes and root words when we teach math. And then the next critical property is parallelism, which I'll reiterate again, this is not beyond young children. Van Healy uses the idea of railroad track sides, and then it becomes clear.
I just imagine also my kids where it's like, hey, walk next to each other and don't collide, versus, you're about to collide with each other. Like, it's a pretty...
I love that. I love that. The embodied cognition. Thank you. Yes, love that. And then the next critical property, as I mentioned, I debated, does it make sense developmentally to do length of sides first or angles first? But because of the need for that transitivity to really be able to understand and compare length measurements on multiple sides, that there's fewer comparisons to make with the angles, especially if you're not trying to get into inappropriate things like using a protractor. If you're just using a non-standard tool of a right angle checker, which I said, I think I got it from Van Healy, then there's just one comparison.
And a big moment that happens in that phase there when you're checking the right angles is you have right triangles can be distinguished from other kinds of triangles, and even going to like acute triangles and obtuse triangles. That's kind of a big moment because you're kind of comparing them to right angles. And another big moment is rectangles
Exactly.
as a special kind of parallelogram that comes
Exactly.
out when you start to realize, oh, these right angles are happening.
Exactly.
Yeah. So there's some
Yeah,
big moments in that critical phase with the right angle comparison kind of thing.
exactly. And if we think about, we all know it takes more than one example to learn something. And that's just common knowledge, but it's also cognitive science, right? That like multiple repeated examples. So if you're experiencing whether something is a right angle or not for triangles as well as quadrilaterals at the same period of time, I mean, it's an open question, but I can't imagine it's not going to enhance learning, right? It makes sense with everything we know about cognitive science that if you get to test this in multiple ways, that you're going to learn it better so that there's a logical progression and focus. And then the last one is the same length sides. And so now we get to do that with triangles. So equilateral triangles, isosceles triangles, scalene triangles, squares, and rhombi that aren't necessarily squares, but are included as squares. Because one thing to make sure that all listeners know, even in the books that are almost all correct, almost all of them mess up rhombus and say it can't have right angles.
Yeah.
So we really have to, if we've already emphasized this right angle idea, and then we, if we hold off on trying to teach rhombi until we can talk about length in a way that's developmentally appropriate, that's ideal. Now the 3D aspects, okay, well, how do we fit 3D in? Where does it fit? So I did pick the 3D placements based on how they interact with this sequence I thought would work for the 2D, especially knowing the youngest learners are starting at the syncretic level. That let's start with those that kind of approximate a circle. So we can do round and straight. So cylinders, cones, spheres, circles, and then polygons separately. And I realized I haven't said this already, but one of the big complaints Van Healy had, he was a contemporary of Piaget, is that his theory is not supposed to be perceived as a developmental theory. It is supposed to be experiential, that young learners can move through the sequence, and Clements Swaminathan and others have shown that, not this sequence, right, but their own work with shapes decades ago, that young learners can know more than older learners or adults as long as they have the right experiences. So that first column, the 3D, first instance or first set of experiences, the 3D shapes that are compared to polygons I just mentioned. And then the next category, when they're thinking about counting sides, the 3D shapes that I brought in are those that seem like triangles because sides are triangles or they approximate a triangle. And then in the next column, where we're talking about the property of parallelism, is children get to experience it in the 2D form and the 3D form at the same time. So the idea that we're providing them consistent opportunities of how to compare 2D versus 3D and developing more sense of the properties. And then the next step, once we're thinking about angles, it's not so much because of the angles that I placed the subtypes of prisms in that section. Actually, it was because of the rectangular prisms, because we needed to save rectangular prisms. I didn't put the other prism subcategories earlier so that they could learn all those subtypes at the same time.
I gotcha. So with parallelism, you kind of will see prisms in the sense that, oh, these faces are kind of parallel to each other in this sense of prisms. But then when you get to this stage of counting and focusing on right angles, now you can be like, oh, and now we can actually even specify what kind of prism we're dealing with.
Exactly. And I should be clear that just like Van Healy would recommend, when I say prisms in the general sense, we're still showing students all variations of, not all variations, but multiple variations of prisms. We're still showing them rectangular prisms, pentagonal prisms, hexagonal prisms, and just calling them prisms. We're not withholding certain types to create a limited perspective and then trying to get them to broaden it. We're just going to start to specify in the next round.
Yeah, that resonates with me a lot, which is showing lots of possibilities, but giving it a sort of parent term that applies
Yes.
to all these variabilities, all are part of this
Yes.
group. And then, you know what, later, if we start to notice specific things, then we can give them more specific names, but they will be positioned as special within
Yes.
the larger group. Like, to me, that resonates. And that was the article that I alluded to earlier. That's the same idea there is we want to like include lots of variation and lots of diversity in the big group. And then later, if you have specific terms that you can apply, then sure, that's cool. Like you can have special names for some of the things inside the big group.
Mm-hmm. And that's part of why I partnered with Clarissa, that I didn't have at my fingertips anymore, the ideas about categorization learning and evidence from cognitive science that children are indeed capable of these kinds of things.
Mm-hmm.
So that we could draw on that as part of our justification. And then moving on, so to make sure that cubes aren't taught as a separate thing from a rectangular prism,
Right.
That's what happens in the standards.
Mm.
It says cubes and prisms as though they're not subsets of each other.
Mm-hmm.
So we need to make sure that we're being clear about that for teachers as well as for the children, so that they have the chance to compare squares and cubes and squares and rhombi, that, oh, look, all the rhombi, figuring out, well, these all have the same length sides.
Mm-hmm.
And we can call these rhombi. And so based on the 3D, at that point, it's those shapes that are visually related to squares. So withholding those 3D shape specific subcategories until we have enough properties to understand squares, but we're learning them at the same time. So they can compare the 2D square versus a 3D approximation, right?
Mm-hmm. All right. Well, it's been great thinking about it. And I, always appreciate your thoughtfulness. It's amazing, right? These are these shapes that are kind of considered basic and like child's play, it's like, no, you can actually for years give very scholarly thought to this and very careful thought to it. And I appreciate you doing that work. I am curious what you see as next steps for this, like who you're hoping uses this or, what you have in mind next.
Well, I'm excited already with some of the response. One of the reviewers had said, I can't wait for this to come out. I'm going to use it with my pre-service teachers. And one of my colleagues already used it with a pre-service methods course. And she said they had really good discussions. So even though I didn't write it for future teachers, the way we wrote it, intending to address people in psychology and general public, if possible, that with it being open source, I was excited that maybe it could influence people beyond, I hope, scholarly activities. But Clarissa and I are definitely working on testing to find evidence for this. There isn't evidence for the standard the sequence that's in the standards. There isn't an evidence base for that. That's just how it's evolved from years past. What I'd love to re-emphasize is the way we started about moving away from simplest to perceive into those that are simplest to define or to conceptualize in mathematically accurate ways.
I've been speaking with Julie.nurnberger.haag. She's available on ResearchGate, and I know you do a really good job of making your work available on ResearchGate, so people can definitely find you there and reach out via email. I'll put that info in the show notes. Julie, I think this is your 5th time on the podcast, which now puts you into the lead. I don't know if you realize that or not.
Oh, wow. That's cool.
Mandy Jansen might have something to say about it when she hears this coming out, but she's, I think, at 4, you're at 5. So thanks again for talking. I look forward to seeing you again.
Thanks so much, Sam.
Curious about what you are reading, what studies have caught your attention, or if there's a book or a project that more people should hear about in math education. So this is an open call for short submissions to future digest episodes on the Math Ed podcast. What I'm looking for are audio files that are about 3 to 6 minutes in duration. I'll collect them and then periodically release them in groups to make digest episodes. If you have something to summarize and share, please find a quiet place and record yourself giving the summary. Aim for about 3 to 6 minutes and then send the audio file to ottensam@att.net. And please put Math Ed Digest in the subject line. That's ottensam@att.net. Within your audio recording, I just ask that you officially introduce yourself and then also give full credit to all of the co-authors involved in the work. Thanks in advance for helping to spread the word about Math Ed research, and thanks for listening.